and also the example that I will run during this lecture in the morning. So you can download and probably you can follow even better if you have the PDF under your eyes. So it is. There is a new directory which is lectures, if I'm not wrong, and inside there there are the PDF. Tell me if anything is wrong so that I can fix it on the fly. Can you see it? Yes. No? Yeah, I see that there is lectures. Ah, no, sorry. Ah, no, yeah, Cozzini, HPCTN, and there is lectures. Yeah, and...
6 minutes ago.
Exactly. Exactly, the important fact is there exactly in time. Yeah.
Just in time computing.
And exactly, and then there is also a directory that should be, which is OpenMP. No.
No, you did.
Ah, I did it wrong.
Yeah.
Yeah, I'm sorry. Okay, just then I will fix it. But now in the root you find a lot of .c files, O private variables, O1 share working loop, blah blah blah, and these are the example that I will run now during the lecture.
Yeah,
I'm sorry. Do you want to move them?
in the OMP 101 directory that I created yesterday with the
Yeah, sorry, I didn't see. Okay, yeah. Can you do that while I'm connecting? Okay, thanks. Sorry. Okay, so as first, actually, I have to add one slide, a couple of slides to the yesterday presentation about vectorization, because at the end we didn't have time to talk about that. But in the afternoon we wanted to show you something. So this one. Just before to start with OpenMP, but really a minute. So I told you yesterday that well, late in the 90s, but mostly in the 2000s, vector register became mainstream. But what are vector registers? The concept is quite simple. So they are large and special registers that you can use as subdivided in smaller chunks. But the point is that those chunks act independently. That is the key factor, because the point is not that they are huge. Of course, it's important, but the point is that you can treat those little chunks independently. What I mean is that in a normal non-vector register, what happens is that you have whatever bits you want, okay, doesn't matter, and you can still use a fraction of these registers, for instance half, okay, or half of the half, okay. You can put whenever you want, you can shuffle bit, whatever. But if you have two of these registers, okay, and you, for instance, add them, what happens is you are adding the entire register, not just one of the section of these registers. Okay? For instance, it means that you have a reminder here. Okay? In a vector register, instead, these chunks are independent. Okay? When you are using, you have different instruction. If you want instruction, if you want to use this register as a whole, enormous one, or but actually not, because you have fixed type. Okay, so 8 bytes a double, or 10 bytes for long double, and so on. Let's say, or if you can say, okay, I want to use these registers as a stream of doubles or float, so you will have twice as numbers, or short float, so you have again, okay, twice as before, and so on. And when you perform an operation on this register, then you are performing n separate operations at the same time, and there is no reminder here. Okay, that is the point about vector registers. So vector registers have been introduced late in the 90s. They were the famous MMX extension of Intel. They were mostly about integer operation because they were meant for graphics basically. But then they evolved in there was the SSE, SS2, 3, 4, and then now we have on the AVX, AVX2, and AVX 512. 512 means that each register is large 512 bits. Okay, so if a double is 64 bit, okay, then you have as much as 8 doubles in a single register or 16 floats. So you can perform, for instance, 8 summation at the same time with just one instruction and in one clock cycle. Okay, that is the huge advantage, of course, of vectorization. And that is what is called SIM, single instruction, multiple data. Right. So this is as I said,
excuse me.
Yeah.
In a superscalar situation, you have two addition in a single cycle or not?
No. So
Because yesterday we saw the
you can. That's a different concept in the sense that you have multiple register, AVX register. So if you are able to, if you have 4, for instance, you can put here and you have the other 2 here, no? And then you can perform an addition. Okay. There are CPUs that can perform, that have 2 ports to dispatch to the vector registers, but it's not that common. Okay, it's not that common. Normally, when you count the peak flop performance, you count just one of these operations. And this is just a pictorial view. So this is for SSE data, for instance, and this is for AVX data registers that they are twice as long as SSE. Okay, and then AVX 512 are longer, and now they will go for, of course, 1024 bits. Okay. And there are special instruction. Probably I don't know whether we have time to go deep in this. Just I think that Stefano, you wanted to show an example in which the compiler vectorize.
Example again in the
Okay.
directory that
Okay.
because
Because
the register.
yeah, there are 2 different approaches. Either you let the compiler to vectorize your code, or you vectorize the code explicitly. The second, of course, is harder. However, it's not that simple to for the compiler to vectorize a loop. Okay, it's quite difficult, maybe quite difficult. But let's postpone this in the afternoon. Okay. So, okay, but I mean, here the key concept was the very nature of the vector register. So the critical point here is that you can subdivide those registers in chunks, and those chunks are independent. Okay, that is the point. Well, so now let's go for parallel computation. Okay. Well, so let's go for introduction. This is the outline. Yeah, sorry. I forgot. So this is the outline of the introduction, actually. So this is a quote that I've taken from a document of the Department of Energy of the United States, and since several years ago, but actually this is even more true today. And we really need orders of magnitude greater computing power than we have at our hands now, just to face the problems, okay? And actually computing power density increased steadily in the years, okay? This is the flopped clock cycle, okay? See, there is a steady increase, and actually at the same cost per flop. No? This is the the flops, floating point operation per second, per dollar, or okay, $1,000, whatever it is, which is, I mean, here in the academy seems okay, well, per dollar. Actually, the world works like this. No, that's an important factor, actually. And so you see, I mean, it's quite fascinating how the computing density, at the same cost has increased in the last decades, okay? And however, in a quite famous article by Harlan Sutter in the Dubs Journal 15 years ago, there was the statement, the free lunch is over, okay? But at first, we know that there ain't no such thing as a free lunch, okay? So free lunch was never been there probably, but what is free lunch? So this is the top 500, which is the list of the most powerful 500 HPC facilities in the world in the years. So this is the average, this is the minimum, and this is the maximum computing power, okay? So kind of steadily increase. You see that here there is actually kind of flattening, no? So, I mean, the numbers are quite impressive because, I mean, you have in the 1994, you are at the gigaflop, something that even my phone can do nowadays, you're also, and then nowadays we are, so 1 teraflop was the most powerful machine in the world, now you have in a single chip, okay? A Tesla, whatever it is, can do that without any kind of worries. And nowadays we are, well, here it is quoted 1 exaflop actually. What is exaflop? Exaflop is 10 to the 18 flop per second. That's not true actually, okay? And that is a key point. So, and actually, this is the peak performance, the theoretical peak performance. This is how they perform on the LIMPAC and on HPCG, okay? So on the LIMPAC, the Summit performs at 122 petaflops, okay? So, and which HPCG, which is kind of 95% of its peak performance, so which is 0.1 exaflop. Actually, with HPCG, it is 3 petaflops. Ba-bang, okay? So what's the difference between LIMPAC and HPCG? Basically, LIMPAC is about crunching number as crazy on place. So you don't move memory, you don't exchange messages, okay? You just dispatch the work, and everybody is just crunching number as fast as possible, and then you collect the result. More or less, this is LIMPAC, okay? So, okay, here you are just basically summing up the theoretical peak performance of all the cores that you have, and you have several millions and millions of cores. Fine. Then, when you go for something, this matrix, multiplication, decomposition, blah, blah, blah. So you have message passing, something that is more real, okay? Then, actually, your performance just drop down, okay? So, something which is more or less exaflop, absolutely it is not, okay? We are at the petaflop still. So 1,000, a factor of 1,000 less. And Pittsdane, the fifth in the list, perform at 0.5. So here, I mean, it's not that much difference actually when you go to the, but I mean, this guy costs, I think, 100 times more than this, right? Well, what's going on there? Because this is, I mean, this is an introduction, but it's important that you catch the point because it's what the challenges that we are facing in the next future and the reason for the actual architecture that we have seen yesterday. So why that architecture is here to stay for a long, long time. Okay. So what is the Moore laws? Actually, everybody knows about the Moore's law. The real point is this one. So every 18 months, the density of transistor in the same area will double at the same manufacturing cost. That is the Moore's law, actually, and has been quite respected for decades. And however, we know this. No? Every scientist actually knows this. Financial doesn't know this, but every scientist does. So all exponential growth get to the end, and that is what happened more or less here. Okay, something like 10 years ago or so, more 15 years ago. Sorry. So this graph is here. You see that typical power that what is used by a socket, an entire socket. Okay, so from basically 1 watt in the 70s up to 100 watt today. Here you have the frequency in megahertz, so from few megahertz, okay. When I was child, I was basically here, okay. 33 megahertz was amazing, okay. Something like wow, and then actually we grew up very fast, and then you see here there is a clear flattening. In fact, you don't buy a CPU with that is faster in the sense of gigahertz since 15 years, more or less. You are stuck there, 2 gigahertz, 3 gigahertz, that is. Okay, that's it. Here is the single thread performance in integers, okay? And here actually is the number of transistors on the socket. So you see that actually the number of transistors is respecting the Moore laws. So what's happening here? No? That's a curious point. So, well, that is basically the same thing, but with just the name of the sockets. But, well, the point here is that you see that these two lines are basically the same. So what happened is that you have, yes, more transistor, but even more cores. And here you had just one core. So something happened here. They started to put more cores in a single socket. So why is that? But these are, of course, profound consequences, okay? So the Moore's law is not over, even if there are rumors. These are all, I mean, I found this quite funny because this is all the, in time, not all, some of the times in which the Moore's law has been declared dead, and with a lot of reasoning about why, and clear also forecast about when it will be definitely dead and so on. So that's since, I mean, 1995, even himself, okay, say no, the law is broken now. But it's still there, actually. So processors are continuing to become more powerful, but they are increasingly differently more powerful. So actually until half of the 2000s, so 2004, 2005, the engineers succeeded in gaining performance by essentially 3 ways. 1, increasing clock speed, so the frequency, the gigahertz. Okay? 2, optimizing execution of the instruction inside the CPU. We've seen something yesterday, out of order, pipelining, and so on. And 3, enlarging and improving the cache. Okay? Well, now, why is this? Because you get more cycles per unit time. Okay? If you have exactly the same chip, but it performs the same operation, but at 1 gigahertz, so 1 millionth time per second, okay. You double the gigahertz, you have 2 billionth time per second, so you just are 2 times faster. That's it, okay? Very simple. So that is possible because you shrink the transistor. So it's basically the fact that the electrons can travel, have to travel a much shorter distance. That is, okay, simple enough. So optimizing execution, blah, blah, blah. Okay, what you have seen yesterday, actually, have you heard about Meltdown and Spectre? Yeah, that are related exactly to speculative execution. Because do you remember that yesterday I've told you that there is the C-move instruction. So facing a branch, you don't choose. You take both branches, no? And actually, and then after that, you decide. The point is that when you do that, you may have, it happens that you may have to access some kind of memory. For instance, let's say that you are proving this pointer, is it null? No? So the memory has been allocated. If yes, do something on that memory. Otherwise, don't do something on that memory. Do something else on some other memory. But you are taking both branches. So what if the memory was not allocated? So the pointer was null, or with crap inside. You are taking a branch, accessing who knows what. That is the point. So clever people can make that pointing at some malicious allocation because in doing that, the CPU itself lower the protection of forbidden memory addresses, because it has two. No? And so that is the very nature of meltdown spectre faults. Okay, don't know whether or not you did know this, but they are related to, this, kind of race of this this complication, and they have consequences. Okay, that just so this is okay, don't worry, and okay, improving cache, but we have seen what it means yesterday. Okay. However, since 15 years, the game performance is essentially due to fundamentally different factors. So, multi-core and multi-threads, the cache, and hyper-threading. We were talking about hyper-threading yesterday. What is hyper-threading, actually? Hyper-threading is related to the ability, to the superscalarity of the CPUs. So, you have different ports, okay, and different pipelines on each ports. So hyperthreading is basically the fact that if you are running 2 threads, no, on the CPU, then the CPU is able to understand that his thread is doing multiplication, and this thread is doing memory fetching, for instance. So I can execute on different ports the same instruction at the same point. But it is not that I'm executing 2 threads at the same time. Some of the instructions that are independent and that do not conflict are executed on different ports at the same time. Okay, that is hyperthreading. It is different than having 2 threads that are being executed at the same time. Very different. So hyperthreading is something clever, but it's not related really to HPC. It's more for desktop computers, just to be more fluent or whatever, but not really HPC. So, point is, 2 cores at 3 gigahertz. Are basically 1 core at 6 gigahertz? Of course not, because you have to coordinate for cache coherence, for instance. Okay, you have threads coordination, you have memory access of the cores to take care of, and you have increased algorithmic complexity. Okay, when you go parallel, you have an increased algorithmic complexity. And that is an overhead. So absolutely it's not true that 2 cores at 3 gigahertz is basically 1 core at 6 gigahertz. That's not true, for a number of reasons. And, actually, most probably the free lunch is over, more or less now. Yes, okay, it's one more time that we say that free lunch is over, okay. But actually there are some physical arguments for that now. And so Moore's law, as I told you, is this, okay? So manufacturing cost per area is constant while the transistor dimension halves every 2 years, more or less. And then the number of transistors doubles in a CPU, fine. But then there is the Dennard scaling, which is related to physics, okay? So basically it says that the power density remains constant, okay? So it's this. The power consumption is the capacity times the voltage square times the frequency, okay? Well, so the linear size of transistors shrinks, and so do the voltage, and so you can increase the frequency, okay? And everything should remain basically constant in an optimistic world. What happens in times is that actually frequency increased by a factor of 10,000 from megahertz to gigahertz, and the voltage shrink by a factor of 5 actually. So more or less the power get higher by a factor of 30 or 50, depends, no? More or less. So the point is that now we are hitting what is called the energy wall, okay? So basically the risk is that if you increase the frequency, you just melt down your CPU. That's the point, okay? And that's why, in fact, the clock rate and the power that is consumed by a CPU just flattened, okay, in the years. And this is a very fundamental point, okay, physical point. So the point is that the Dennard scaling has broken down due to the leakage current. This is basically a quantum effect, okay? And the threshold voltage, the point is that you cannot lower the voltage that much because otherwise you become too noisy, okay? So there's not enough energy to to draft the electrons, okay? The electrons start to be confused, no? It's kind of voices, no? There are rumors in a room. If I talk loud enough, you can hear me. Otherwise, you cannot hear me. That's basically this. And yeah, some other physical limits at the atomic scales, because now we are doing, 7 nanometers, you know, more or less we are 10 nanometers. Is basically the scale between the gate, you know, and the transistor. No? The point is that an atoms is almost, we are basically 20 atoms in there. No? So it's not that clear how we try to overcome this kind of difficulty. It seems that now we are really hitting the physical limits of the Dennard scale. So it is not the Moore's law that has been broken. It is the Dennard scaling law. But they are, working together, right? The point is that you can put more transistors, but they don't work. So it's totally useless. And this is the energy, actually the so-called energy wall. The point is that here we are almost at the density per square centimeter of a nuclear reactor, actually. We could hit that if we increase the density of computation, right? Well, so many core CPUs are here to stay, okay? So the point is that here you are not powering all this area at the same time, okay? So that has been the trick. But this has consequences. So you have to consider concurrency-based model programming that is different than parallel and instruction level. So you have to think about subdividing the work in as many independent tasks as possible. So the attention is not on procedures and instructions, but on data and relation between data and the operations that you have to perform, which is a totally different approach. And you have to take into account that increasingly we have specialized heterogeneous cores, so GPUs, FPGAs, and different cores inside the same CPU, and so on. And multiple memory hierarchies, but you already know about this. So, well, now I'm just reading. So Sunway performs some application at 10 petaflops, and it consumes 18 megawatt. 18 megawatt. I think it's like your whole city, more or less, just half of the city, right? And simply scaling to exaflop, you will need a nuclear power plant, okay? Gigawatt is the energy scale of a nuclear power plant. Seems quite exaggerated, no? Just to perform calculations. So the exascale goal actually is to reach the exaflop at 20 megawatt of energy power, so 50 gigaflops per watt. Okay. Nowadays we are, and rule of thumb, 1 megawatt is 1 million. Okay. So it means that these guys consume about at least 20 million of electricity per year. Right? So nowadays we are more or less, now this is old. We are about at 10 gigaflop per watt, more or less. So we are far away. And what is consuming memory, actually? What is consuming memory? I would have guessed years ago that it was, calculations. It is not. It is memory. Okay, it is memory. This is in picojoule, how much energy you consume. Okay, so to perform a double precision floating point operation, to read the registers, and then increasingly to go to the memory, okay? DRAM and in the network, of course, that when you connect more CPUs. So what is power consuming is the memory. So I've collected this data about the memory chips, blah, blah, blah. So if you want to feed 1 byte per flop at 10 to the 18 flop per second, you need, with these very performant DRAMs chips, 28 megawatt or 60 megawatt, just for the memory, okay? Just for the memory. Well, why I mentioned the byte per flop? Because you can characterize the scientific codes with the arithmetic intensity, okay? So how many calculations you perform on each byte, So a code is more arithmetic intensive if you perform a lot of calculation on the same numbers, basically, or not if you just move in memory. Okay. So big data are basically have a small arithmetic intensity, whereas, for instance, well, particle methods have, or dense linear algebra has very, very large arithmetic density. For instance, particle meters. If I want to solve a Coulomb interaction, so n square, I have to perform, let's say, for instance, gravitational, no? Because for electromagnetic, I have a kind of shield, no? Because it's then it's all neutral after a short range. But gravitational, I have to exchange information with the whole universe, basically. No? So if I have n particle and I want to sum up with the direct calculation, this n square. You cannot avoid this. So it means that it increases like the with the number n. So I have with my byte, which is my position. Okay, the byte is the position. So okay, 3 doubles. Okay, on my 3 doubles, I have to perform the distance between all of you. Okay, so it is okay, the difference of the x, y, z, and the square, and then sum up, and then the square root with all of you, and then sum up. So a lot of calculation on the same bytes. So this is arithmetic intensity. Okay. And typically, so it is 1 byte per flop is a threshold to be classified as arithmetic intensive, right? So this is the how many byte per flop you have in HPC facilities in the top 500 historically, and you see that nowadays we are really dramatically dropping. We cannot feed. I mean, so the computing power, calculation is not the problem. The point is that to feed that power with bytes, okay? Both for energy constraints and also for, I mean, what you have seen yesterday, no? The point is that it costs cycles to reach the data. So it's not that easy to feed your computing power. So these then have some consequences about how you program, no? Because many people, probably 99% of the people and scientists, are stuck to the von Neumann model and are not aware of everything about this. And so you write programs in a way that is totally unfit for what is the reality today and will be reality in the next years, okay? So you have absolutely to change your mind, because this is so task decomposition and scheduling, memory locality and hierarchy, and massive plus fine-grained parallelism. Okay, this is, but these are the 3 pillars basically, right? Okay, just was an introduction. Well, so what is parallel computing? Of course, parallel computer is a computational system that offers simultaneous access to many computational units fed by memory units. Okay, the computational units are required to be able to cooperate with each other, communicating in some way. Okay, this is parallel computer. Parallel processing is the ensemble of the techniques and algorithms that makes you actually able to use a parallel computer with a code that is suited for. Okay, just to begin with some definition. So. Parallel processing is expressed by software entities that have an increasing level of granularity. Processes, threads, routines, loop, instructions. Okay, these are all different things. Main point here are processes and threads. How many of you know the difference between a process and a thread, for instance? There is a slide in a minute of that, but that's important. Okay, so those software entities actually run on computational hardware entities, so processors, cores, accelerators, FPGAs, okay? And the data to be processed live and travel in storage and on the network, actually, okay? So on the memory, on the cache, non-volatile memory, they travel in the networks and you access them, for instance, by message passing or direct memory access, for instance. I mean, it depends on the architecture that you have underneath, okay? And the exploitation of the hardware resources, these ones, is concurrent among the software entities. Okay, so kind of complicated environment. So this is just a pictorial view. So you have processes. Say process, you have threads. Each thread has routines, and they live in CPUs that are many cores with caches, private caches, and they access some RAM that is in well, or on the same board or over the network. Okay. Well, why parallelism actually? For two reasons. Because for time to solution, so you want to solve the same problem in a smaller time, or you want to solve a larger problem in the same time. Okay, there's two different things, right? Or for the problem size. For instance, let's say that you want to on my field, you want to perform a simulation with 10 billion particles, and each particle needs something like 500 bytes. How many memory is it? How many? Can you really have that many memory? Even, I mean, geometrically, you don't know where to put it on a single board, no? So the problem size also calls for parallelism, okay? So what is actually parallel performance? Because, okay, everything is good here, fantastic, but is it efficient, no? How can we define efficiency? So, performance is a tag that can stand for many things, but in this frame, performance actually is the relation between the computational requirements and the computational resources needed to meet those requirements. So the resources are the hardware, is the time is a resource, energy is a resource, okay? I mean, we are start seeing that there are differences in the way you code and the energy that you consume, actually. That's quite fascinating. And money, of course, this is also a resource. So the performance is the inverse of the resource, more or less. No? So the performance ratios is the ratio of the resources that you want to use. So, well, just let's start. Put some equation about what is performance. The key factor, so n is the problem size, t is the time, serial or parallel, and this depends on the problem size, okay? P is the number of computing units. This 1f is the fraction of the serial part of your code. So you have a code, not the whole code is parallel, okay? There always is some part that is serial, no? Sequential. And this is the parallel overhead. Okay. So the speed up is the ratio between the serial and the parallel time. Okay. So of course you do expect that this one is smaller, so the speed up is larger than 1. Okay. So it is half than this, and then you have a speed up of 2. Fine. The efficiency is actually the speed up divided the number of processes that you have. So kind of, you do expect that this is 1 for a perfect code, okay? Because let's say that for a perfect code, this one you use 2 processes, so you are twice as fast, so the speed up is 2, you divide by 2, so you have 1, okay? And so on. You use 4 processes, so you have 1/4 of time, and then here efficiency 1 again, okay? This is the perfect code. I mean, that's kind of magic, yeah. By definition, okay, yeah. Well, with this definition, of course, the only way is that you have a speed up larger than 1/p. Okay? It might be some algorithmical dependence, but I mean, I'm not aware of any case about this. Well, naive expectation. Okay, you say if a single processor has m megaflops, parallel flops performance with p task is p times m. Quite, I mean, legitimate expectation actually. If the sequential runtime is t, parallel runtime is t/p. Legitimate. If parallel runtime with p task is t and the runtime with p1 task is t1, then this is the ratio, so it scales. Okay, this is called scaling, basically. Okay, and scaling with the number of tasks. So this is strong scaling, and if parallel time with p task and problem size z is t, the runtime with size z1, again, it scales, okay? So this is weak scaling. Is that correct? Of course, no, because you're clever people, otherwise you wouldn't ask it, huh? Well, so let's say that the sequential execution time is the time that it takes for the size n and one processor times the serial fraction plus the same time times 1 minus serial fraction. Of course, this is the t, okay? But this is useful afterwards. So, assuming that the parallel fraction of the computation is perfectly parallel, okay, we can say that if we use p processors, okay, we act only on this part of the code, and it is perfectly parallel means that this one is divided by p without any kind of difference, okay? Plus actually an overhead. That depends on the size. I'm sorry, this is p, not t. It depends on the size and on the number of processors. What if, for instance, the overhead? Communication. Let's say that we are sharing some work, summing up an array, okay? Then what is the simplest thing that we can do? We are, whatever, are 20, so you take the 120, blah, 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 no? And then that we have to communicate at the end, okay? This is overhead, okay, for instance. And it grows with the number of people, right? But then you are clever. For instance, you may say that, no, just communicate by power of 2. So the 2 of you, and then one of the 2 of you with one of the other couple, and then one of the group of 4 with the one of the other group of 4, and so on. So you have log 2n. The overhead is log 2n instead of n, for instance, no? So it becomes complicated, this way. And then, so the speed up is, yes, this one, as I said yesterday. So with a little bit of math, okay, I'm not boring you with that. So if f is the f now is without the n, so it is independent of the size of the problem. That's important, okay, because this was the first assumption that has been done in this calculation. So we have this speed up, which is bound by 1 over f, so by the serial fraction of the code. This is the Amdahl's law. It says that you cannot have a speed up larger than 1 over the serial fraction of the code. And I mean, this is in the number of processes. So if you have a serial fraction of 0.1, so 90% of your code is parallelizable, you can have a speed up of 10, but with an infinite number of processes, okay? If you have 0.9 serial, no way. I mean, it's stupid to use 30 processes. This is what Amdahl's laws say. And that's true, I mean, under this assumption. So that f doesn't depend on n, okay? But actually, there are some significant issues with the Amdahl laws. So this is quite depressing, okay? This was a debate actually in the 60s. This was against the parallel computers, because Amdahl said it's totally crap, because all the algorithms, all the parallel world was at the beginning at that time, no? But he says, I mean, come on, what you are, this kind of stuff, so what can you gain? Just perform better with your code, or make better hardware, no, at that time. So it was against parallel computing. And however, the point is that the problem size is kept fixed when estimating the possible speed up with the number of processes, which is called strong scaling. However, most often the problem size scales as well, actually, right? So, this is pessimistic, actually. This is optimistic, because the parallel overhead is totally ignored, okay? The point is why is it optimistic, this one? Because normally the fraction of sequential part may decrease when the problem size increases, which is actually what happens, no? When you increase the size of your problem, you don't increase the whole problem, you increase the parallel part of the problem. So what I'm increasing, the number of the amount of numbers that I want to sum up with you, not the paper, and so the sequential part, not entering in the room, okay? Because you are in the room, and I'm entering the room. That part is still there, okay? We are just a larger number, then there are larger people. Okay, of course, if the numbers are just 100 and we have 1,000 people, it's totally useless. But I call 1,000 people when I have 1 million numbers to sum up, not when I have 1,000. Okay, so that is what happens. And in fact, with a little bit of math, the point is that you consider that the workload is A plus B. A is the sequential part, and B is the parallel part. But then, when you have P processes, you give to each process is B, no B over P. Okay? So the total amount of work is actually A plus B times P. Okay? And so it is still using the same amount of time. So actually now you have a speed up and you end up with a Gustafsson law, which is this one. Okay? So you have the speed up is now bound by P. So it's linear. Okay? Of course, real world is something in between. No? But now you have a clear justification, well grounded for parallel computing. Okay? So these two lines of reasoning, the Amdahl's law and Gustafsson law, are related to two different problems that are real, actually. So the strong scalability is when you fix the problem size and you increase the number of processes that work on the problem. And the weak scalability is then workload is fixed, so not the size of the problem, the workload. So the part of the problem that you assign to each process and you increase the number of processes. Okay? So these are two different concepts, strong scalability and weak scalability. It is almost, I mean, it's very difficult that a code can have both optimal scalability in both cases, okay? Because it depends on the problem that you are and on the algorithm that you choose. And well, then there is the parallel overhead that is quite significant. You remember this is, so then we have this, okay? And let's define, so what is the parallel overhead is difficult to define analytically because it depends on the algorithm, depends on the problem, a lot of stuff, okay? So we can measure it actually. So let's define an experimentally measured serial fraction, so which is the time that you that it takes to run plus the overhead, the serial time plus the overhead over the serial time plus the parallel time. Okay, so because the overhead is considered to be serial time. So I have made some experiment. Let's say that you have you observe this speed up with 2, 4, 8, 10, and 20 processes on some problem. Okay, yeah, with a little bit of math, you end up with this formula for this. So you have this speed up, okay? So it is not optimal. Of course, you don't have 20 here, right? And so you can measure this, and you find that what you have is a constant experimentally measured fraction of time, serial fraction of time. So the point, this tells you that the overhead, the parallel overhead, is not significant. This is really limited by the serial fraction of the code. And in fact, if you have 8.18, if you made the calculation with the Amdahl's law, you end up with this, basically. Okay. Now there's a different case. You observe. This is observed, okay, what you observe, the speed up, okay, which is different than now. And you find that this quantity increased with the number of processes. So this tells you that there is some parallel overhead that works. Actually, it is because it was a communication that scales like P inside this problem. Okay? And if you increase P, you increase the overhead.
Like is the 3.50 correct, the number?
Yes. Yeah, because the point is that when you have a parallel overhead that scales like P, if there is a threshold, if you increase the number of processes over that threshold, the parallel overhead is starting to dominate, and then your speed up goes down. Because you start to pass more time in communicating, for instance, than in computing. Right? And then at some points, if I had to put this to 2,000, basically, it could even be that you have a... Yeah.
That's what happens when you put like pragma OMP at random in your code before.
We come to this in a few minutes, starting to talk about OpenMP.
No, but I mean it's caused by this thing that you just said.
It might be, but let's arrive at the point.
Okay.
Okay, so sorry, this was a relic. Okay, so let's start to talk about OpenMP, okay? Yesterday, Stefano told you something about the different parallel programming models, okay, so I'm not spending time on this. So just saying you that, I mean, you use MPI when you want to communicate among processes that runs on hardware that have no direct connection but the network, okay? And you use OpenMP and similar stuff actually when you are in shared memory. So when all your processes are running on the same board, okay? So they share the memory. Every process can access all the memory that all the other processes can access, okay? So you have two different words. Inside a single node, for instance, of your cluster, you can use OpenMP. If you are running on two nodes, you cannot use OpenMP because they cannot see each other's memory, okay? There are models in which you have a kind of unifying view of the memory of the whole machine. They are called PGI, okay? Global Address Space, okay? The GAS model. So, but there's another different stuff and so on. So let's concentrate on some basic introduction on OpenMP, which is very effective and very quick to be, it's very easy to be productive and quite quickly. So actually, just a couple of slides about the difference between threads and processes, okay? So what is a process? It is an independent sequence of instruction and the ensemble of resources needed for the execution. So you know that a program needs much more than just the binary code. It needs a memory region, okay, that the operating system gives to him. Then he needs access to system resources, the files, input, output, whatever. So a process is the ensemble of the code, of the memory that it needs, and of the interaction with the machine. So then you already know this. A process have a stack, a heap is the code that it has counters, okay, in the registers, the instruction counter, the stack pointer, and so on. You may have different instances of the same program that run as different processes, okay. So you can have two Emacs open on your computer. There are two different processes, okay. A thread actually is an independent instance of code execution within a process. So the point is that this is a process. You have one heap, you have one code, okay? So one virtual space of memory, okay? And then you can spawn several threads that share the stack, okay? But its own has its own stack. That's the point, okay? Each thread has its own stack, but access the same code and the same heap, okay? So they share the memory, but they have a private stack, right? So this is the difference between, the point is that to create a process, I mean, takes time because the operating system has to perform a lot of operation. To create a thread is kind of 1 microsecond, basically. It has to perform some operations too, of course, but it's much faster than creating a process, okay? And, well, nowadays, in the computation unit is a core, basically, okay? So inside the same CPU, you can have where the threads live, actually. They can live inside the same CPU where the further processes live, or even in other sockets, so in other CPUs that are in the same NUMA area. The NUMA is non-uniform memory access area. So the board, basically. So at your board, you have how many sockets do you have on a node of your 4? Okay, so you have 4 sockets. Inside each, you have, I don't remember how many cores. 18 cores. So okay, you can have a process here that spawn threads, and you can tell to the process to spawn threads, or either inside the same socket or on the other sockets actually. So you can have spawn 4 threads, 1 for each socket. Okay, you can do that. Okay.
Would that be efficient?
It depends on what you want to do. It may be. But we see that in the afternoon when we have exercise about OpenMP and exactly how to place the threads, because you can control this, okay, tightly. You can control that. Just to give you an hint. So you have your node. So you have your board, sorry, and you have here is the memory, okay, right, which is shared. Here you have your 4 sockets. Each one has its own memory channel to the memory with a limited bandwidth. Enormous, of course, because you have very good hardware, blah, 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 but limited, right? So if you have 4 threads here that wants to access memory, they have to share this bandwidth. But if you spawn a thread to each socket, so you have 1 thread here, 1 here, 1 here, 1 here, and they have full bandwidth to access the memory, for instance. So it depends, okay? Okay, then, say, what is OpenMP? OpenMP is a standard. It's not a program, okay? It's just a standard. It defines, is a book. OpenMP is a book, okay, where the API are defined, and then who is actually converting your code is the compiler. So you must have a compiler that supports the OpenMP standards. GCC, ICC, and PGI, all of them supports for sure up to OpenMP 4.5. A few months ago, they released 5.0, okay, which is a great, step beyond. But okay, so the running model is this one. You have a master thread. You have limited parallel regions, okay, inside your code that you have to define. They are very well defined by the pragmas, okay. So the model is that you have 1 thread, so which is your main process, okay. The main process is also a thread. So you have your main thread that at some point create a parallel region. It spawn child threads, okay. They perform some work, and then they rejoin, and then you continue with serial work, and then you spawn again, and so on. You can nest parallel regions. For instance, this thread here is creating another parallel region and another 3 threads, and then this one again, okay? The point is that, it's risky because here you have a lot of overhead, okay? So it can be done. It's called nesting. It can be done. It's in the running model of OpenMP. So the point here is that threads access and modify shared memory regions. Okay, all the threads access the same memory. So it's up to you that this access is safe and correct. So you have explicit or implicit synchronization that protect against race conditions. We'll see everything we will be discussing in the next slides. There is no concept like explicit message passing that you see tomorrow. So 2 threads, do not communicate with each other with sending a message, okay, a ping. There is no such concept. And that is important. So loop carry dependencies hamper any parallel speedup. What are loop carry dependency? We'll see, I don't know whether in the afternoon or tomorrow, but that's an important point, so I want to show you something. And the shared variable attributes are vital to reduce or avoid the race conditions. What is a race conditions? Is when between 2 synchronization points, at least 1 thread is writing a memory location that another thread is reading. That is a race condition, because then you don't have any kind of coherency, because the thread that is reading should read before or after the writing, okay? So you must avoid the race condition, okay? This is ill-defined behavior. And each thread performs its part of parallel work in a separate space, so the stack that I told you, okay? And its stack is not visible to the other threads. So the private, there are 2 fundamental concepts. There are shared variables and private variables. Shared variables are they may live in the stack of the fodder process, which is accessible by all the children threads, okay, or in the heap. But the variables that are private, so that live in the either in the stack of the thread or in the heap but have been allocated by the thread, are not accessible by the others. Okay. On the heap, yes, but then they must know the address. Okay, so it's a little bit complicated. And the number of threads, so how many threads you fork, okay, can be dynamically changed before a parallel region. So you have environmental variables, and where is this? No, okay, well, you have some environmental variables that will show you and that control the behavior of OpenMP. As first, how many threads you have to spawn. If this variable is not given or defined, by default, the number of threads that are created is equal to the number of cores that you have on the socket of the fodder process. Okay, so the fodder process is running on a socket with 18 cores. The default is that you spawn 18 OpenMP threads. Okay, but you can change this with environmental variables or inside the code. So you can have different number of threads in different parallel regions in the same code. Well, so how you program OpenMP using directives. This is in C, this is in Fortran, okay? So an OpenMP directive is a specially formatted pragma. Pragma means pragmatic advice that you give to the compiler, okay? And most of the directives apply to structured code block. It means a block of code that has a single input and single output, okay? And you cannot branch in it, outside of it. So it's forbidden. For instance, if you have a for cycle in an OpenMP region, you cannot jump outside of the cycle, okay? You have to handle these situations in a different way. I forgot to put a slide about that. Okay, I will add and then I will upload the new version, okay, tomorrow I'll tell you. Because this is something puzzling. Many people don't know and don't know how to treat, okay, this fact that you cannot jump outside of a parallel region. So, but sometimes it happens actually. So these directives allows to create team of threads, manage the sharing of the workload, because, okay, you create the threads and then you have to dispatch the work. No? How can you do that? Of course, we'll see this in a minute. You can specify which memory regions, which as the variables are shared or private, and you can drive the update of shared memory regions. If actually, okay, let's postpone this to the examples, and synchronize the threads. Okay, because in time to time you have to synchronize. Okay? For instance, if you want to sum up all the entries in an array, at some time you have to synchronize. Okay, so you can extend dynamically. So the region, the parallel region. So let's say that you have this. Okay, this is a parallel region enclosed in braces. Okay, this is typical OpenMP parallel region. You create a parallel region just like this. You put a pragma OMP parallel, 2 braces, and automatically you know that the compiler for you will put here all the machinery that is needed to create the threads. In this case, the number of threads created will be either the value of the environmental variables that you have defined in the operating system or at the shell, or the number of cores that you have. Okay. Here you are calling a function actually, right? So this is a dynamic extend of the parallel region. So in this this is the function. Inside the function, actually, you can have another pragma, okay, for instance. This is called an orphan directive. So, all in all, OMP is made of 3 main components, basically. The compiler directives that you put in the code, the runtime libraries that let you perform a number of stuff, and the environmental variables that let you control the behavior of OpenMP in different situations. So mainly the number of threads that you have to spawn in parallel region, where to place the threads. We have exercise on that, no, Stefano, in the afternoon. You have this matrix multiplication or APCG with different placing, isn't it? The same that we have in the lectures.
Yeah, let me focus on it.
Oh, in any case, we do that. That's not a problem. So in the afternoon, you will learn about this stuff, and how to bind the threads. So you require the operating system not to migrate the threads, or yes, no. Okay. So you can control the behavior of OpenMP. So the toolbox is this. So you have directives. This one, or yeah, basically this one. So work sharing construction, so you have 4 sections: task and attributes, shared private, first private, last private, copy in, copy out, copy blah blah blah. Okay, some of them will be covered in these lectures. You have synchronization, so critical region, atomic operation, barrier, order, flush, no wait, and so on. And the runtime, so a number of functions that you can use. For instance, you can set the number of threads, okay, dynamically. You can get what is, who am I, so what the number of threads that is calling this function, or the total number of threads that has been called in that parallel region, so a number of stuff, okay. So this is the toolbox of OpenMP, basically. Okay, so first example. Well, to activate OpenMP, you have to put some option. You have to give some option to your compiler. For GCC is -f OpenMP. For Intel compiler is -q OpenMP. For PGI, I don't remember. I think it's -f. But okay, so read the manual. So this is, for instance, a program that uses OpenMP. Okay. So let's say that you have this variable. You put this to 1, and my thread ID is 0. Okay. Then you have also a conditional compilation possibility. So when you define this in your compiler, at command line of your compiler, then the compiler activate this define. Okay, you know what defines are in C? Or, well. So if this is defined, okay, this part of the code exists. If this is not defined, this part of the code doesn't exist. The compiler will never see this. Okay, so this is another more possibility that you have in encoding your stuff. So what happened inside this region is that you create a parallel region. Inside the parallel region, this is an error, for instance. So I've seen this now. Why is this an error? Can you see why? Yeah, kind of. Yeah, that is yeah. The concept is right. So this routine gives the ID. Then basically the ID is an integer number. It is between 0 and the number of threads -1. Okay. So this is meant to be the ID of the thread that is calling this function. So this is put on my thread ID. But actually my thread ID is a shared variable. Okay? So what happens here? Is that an error or not?
Yeah, you try to access that 4 times. I mean n course times.
Exactly. This is a race condition. Actually, it was because I was quite sleepy writing this. This was meant to be here. Okay. And so you have to define this. If you define this here, everything that is declared and defined inside a parallel region is private. Okay. Otherwise, by definition, if you are using a variable that lives outside of a parallel region, this is shared. Okay. So this is undefined. The value, it is not illegal, but the value that you have here for my thread ID is undefined. Basically, is the value that has been given by the last thread that performed the operation. And then here, this is a different pragma. This tells to OpenMP that the following line or the following region if you put the braces, must be executed only by the master thread, so the thread number 0. Okay? And so you have that n threads is, you know how many threads you have in the parallel region. And why is that? Because you don't need that all the threads perform the operation, just one. So Pragma master tells for calls for only the master perform the operation, but it could have been also Pragma single. Single means it doesn't matter who, just one. Okay, which is more effective because this, of course, means that you have to wait for the master. But if the master is doing something else, okay, so in some cases you can consider to put Pragma single, which is more efficient because the first that arrive can perform it. Okay. Well, so I will fix this, or not. I will put here another slide. Okay, that's interesting, but just to keep you awake. So let's start with a classical and very common problem: the sum of an array. Okay. Okay, this is the, of course, the serial code. Well, now what we can do is to put a pragma just outside the 4. So you have pragma OMP parallel 4. This immediate is equivalent to put pragma OMP parallel braces and then pragma OMP 4. Okay, this kind of shortcut is perfectly equivalent. Okay, then I'm starting to use some clauses of the parallel construct. So here we are telling that there is no implicit assumption about the role of the variables, so who is shared, who is private. Okay, so no implicit in this case. So you have to declare explicitly everything. So here I'm declaring that A, B, C, and N are shared, and the I is private. Okay. So 4 is a work sharing construct, and the workload is automatically subdivided by all among all the threads that participate in the parallel region. Okay. So that is interesting. Okay. So let's go to the exercise 0. You can go on your account on the cluster or on your laptop, because I think that everybody has multi-core, no, here on the laptop, so it's not a problem. I'm using my laptop actually now for this quick and dirty point. So why go to the 00 underscore private variables.c. Okay. So this code, I have to show you my shell, of course. Okay. Switch profile, lecture. Okay. Can you see it, or I have to enlarge? Oh, sorry, I enhanced the opacity. Right. So CD. Okay, so YOO. Sorry, I have to close this. Better to close this. Fine. YOO. So private variables.c. So, okay. Yeah, just remember to include the openmp.h. Okay? Otherwise, the compiler will complain about not understanding anything of what you're doing. Okay, so it's necessary that you include the omp.h. Okay, so what's going on here? I just wanted you to convince one stuff, that here we have this parallel region, okay, with a private I. I want to convince you that this I inside here is not the same I that is outside here. Okay? How can I convince you? Just show me the address. I mean, it seems convincing to me. I don't know to you, but if they have different address, they have different memory locations, so it's not the same I. So in doing this, I'm just also showing you just a little bit of trick. I'm just showing you also the stack of the process. This is the way in which you can read the base and top of the stack of your process. This is an inline assembler command that you can give, very simple in this case. And okay, so a part of this, so you just initialize the array. You have two arrays, A and B, and what you want to do is to put the multiplication of AI and BI in CI array. Okay, let me execute this and then we go for the coffee. And or you can also go for the coffee and continue talking as you want. Okay. And so here inside this parallel region, I'm just printing the address, okay, of the variable. So let's see what happens. So well, GCC minus F openmp minus O free. Well, doesn't matter, and minus O. This one. Okay, that is how you just compile, and then. Okay, so. You see that the address of I is this one. Just look at the N6C8, and the address of I for every thread number is different. Okay? No. Yeah, it's different. Okay? So they are different. The point is that if you declare, in this case, back to the slide, in this case you have an I that lives here. But this private I doesn't mean that that same variable is private in all the threads. It means that every thread creates a variable that is named I that lives only in the parallel region, and it dies after. So if we put here I equal -1, outside this parallel region, I is -1 because it's not the same I.
Why is still good programming putting the declaration of I outside?
I would say no.
Okay.
But it's legal.
Okay.
Actually, it is clear. If you know the stuff, it is clear. Okay.
We had the same error before in the slide. With the private I, we should solve the issue that you showed in the previous slide.
Exactly. Exactly. Absolutely. You got the point. And we'll go the coffee.
Sì, 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 perché quindi ha fatto
Però
ha innovato la convenzione.
no,
Perché no, l'hanno appena fatto. Infatti mi ha chiesto un incontro, mi anticipo un po' quelle che saranno le.
prova ad aprirla prima. Questa?
Prova?
Prova a trovarla. Sì. Perché da lì internet
Sì, e potrebbero cambiare anche un po' di cose perché la parte OBDI che noi pagavamo singole licenze in più, cioè che c'era una base del contratto, quindi una cosa in più nostra, adesso l'hanno inclusa nella base. Quindi può darsi che paghiamo qualcosa in meno anche, perché avrebbero messo probabilmente
infatti
prendiamo
vai
un po'
sì,
scontato.
sì.
Comunque
Sì,
dovrebbe
senti una
venire,
cosa,
cioè dovrebbe
hai
chiamarmi
installato il
il
GDB su
questo di VMware per raccontarmi un po' com'è. Quindi poi dovremo
perché io l'avevo
probabilmente,
installato su quello precedente, quando l'ho
non so se ci
installato
faranno
quello
pagare una
che
rata per
uscivo
2 mesi da installare.
no, no, l'ho installato, però dopo quando io chiedevo la variabile faceva così. Cioè, deve esserci qualche problema su Mac con GDB. Io per esempio sono di del Windows.
No, 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 non c'è una toga, c'è un extract. No, ma se fino alla convenzione nuova che aderiamo, poi ci sarà una copertina e.
Veramente è OMP
Sì,
101?
sì, 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 sì.
Com'è?
Veramente
Sì,
è OMP 101.
sì. Okay. What? Okay. So, then we were here, and this was just to introduce how you can use these clauses, okay, for the parallel constructs. But actually, there is a default behavior, so that the variables defined within the parallel regions are automatically private. So we actually don't need, for instance, this private I, but just we can do something like this, okay? So it's perfectly legal. And however, we should ask how the work is assigned to single threads in this construct. You know? If you go to exercise 1, Y01 share work in loop.c. So what it does is, okay, here I introduce this, okay. So it is a global variable in this case, and there is this directive which is pragma OMP thread private and the name of the variables, or if you want more variables, comma and the list of comma and the name of the variables. What does directive do is oops. I'm using the point. I can't with the shell. Basically, this declare that this global variable is private. So actually, what happens is that there are n copy of this variable, and they are all private for each thread. So they are still global. So the point is that when you spawn a thread, it will see its own global variable called ethers, okay, from everywhere. So you have the advantage that you have a global private variable, okay? So you can see, every thread can see its own ethers from everywhere in the code, not just inside the parallel region, because the threads are inside the parallel region. But what if you want a variable to exist in a parallel region and then to use that value in another parallel region? Since if you declare the variable inside the parallel region, then it dies when the parallel region ends, okay? And then what happens? You can use this, okay? So global variables, but private, right? So this is thread private. Not clear? Okay.
When it is useful.
let's say that you have, for instance, this is to keep track of the number of iteration. I could have done differently, but was purposely to introduce this. Okay, so let's say that you have here a parallel region, and you increase that counter for whatever happens inside here, a number of events. Okay, then you have something sequential, that you have another parallel region, and then you want to use this counter, so the number of iterations that happen here is useful inside here. You can do that in a number of ways, actually. One of the ways is this: if you have global private variables, okay, this still exists.
I don't have to write private anymore.
No, in fact, still exists. Okay.
Yeah.
Okay, so this said, what happens is that I just want to show you. Yeah, this is one classical way to propagate the number of threads inside in the code. So you have, this is a normal variables, okay, like you do in the serial programming, and threads, you put it to 1 as default. Then you declare a parallel region just for the master, and you write on n threads the number of threads that is spawned on the parallel region. So here outside, n threads now is whatever it is, 4, 10, whatever it is. Okay, so it's a standard way to have at hand the number of threads that you have in parallel regions. Then what we do here is to have a parallel 4 and to increase the number of iterations. So this is global private. So every thread will increase its own ithers, okay? And then outside, we have another region here, parallel, critical, which means that all the threads will execute this code, but once per time. It is not, the order in which this happens is not defined. There is another directive that is ordered, which means the same, once at a time, but on an ordered fashion. So first 0, then 1, then 2, then 3, whatever it is. This is whatever order, doesn't matter. What is important is that just one thread will print its, the value of its ithers, okay? So there are a lot of, don't worry about this, okay? We will see that later. So now if we execute this, okay, so there is a default here, sorry. So the default number of elements of the array is n, okay? And so, sorry, this is not an array, it's just summing up the first n integers. Sorry, I forgot. So you just summing up the first n integer, no? The Gauss will say n times n plus 1 divided 2. And so n by default is 100, okay? So if you know how many iterations every thread has performed, you know how the workload has been shared, okay? So the default is 100, so you have 25 iterations. You have 4 threads and 25 iterations per thread. So perfectly shared, okay? And the result is, of course, correct. If we want a larger number, let's say whatever it is, then you have a slight difference in work sharing, of course, okay? And still the result is correct. So when you have this kind of construct, pragma OMP parallel 4, you have a default behavior that is actually implementation dependent. So this is the default behavior that has been chosen by GCC, but actually is a standard. So it is equally subdivided workload, okay? So you have the total workload, the total number of iterations, objects, whatever it is, divided by the number of threads. and the first chunk to the first thread, the second chunk to the second thread, and so on. This is the default. You don't have to care about. You can just put pragma and p parallel 4, and you know that this is the default behavior. It is not guaranteed. It's just usual, okay? So you go to your compiler manual, you see what is the default behavior, blah, blah, blah. Normally, it's this one. Well, okay, so then you have different, you have some clauses to change this behavior and to change the how the work is dispatched to the different threads. This happens by the schedule clause, and you have different scheduling types. So static is the one that you just seen. So the work is divided in chunks, fixed size. You can control this chunk. If you don't say anything about this, is equal size. So normally is the number of iterations divided by the number of threads. And it is distributed in circular order. Okay. So let's say that I put there 1,000, okay, and I say chunks 10, then the first 10 numbers would have been processed by the first thread, the second 10 by the second, blah, 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 up to 40 because I have 4 threads. Then from 40 to 50, again on the first thread, from 50 to 60 on the second thread, and so on, and so on, and so on, until you end all the iterations. Another one is dynamic, actually, which is quite different. So the iteration is divided in chunks of size, chunk size. If you don't give the size, then the size is 1. That is very different than before, okay? And the workload is dispatched to the first available thread. So what happens? That you have, let's say, the first 4 chunks in this case, and then as soon as a thread has finished its job, just show up and give me a job, and then typically the master thread just gives the job, okay? Is that clear? Dynamic means that you divide in chunks, and the first one that finishes chunk get another chunk, and so on, without any particular order. Then you have the guided type, which is similar to dynamic, but is different in the sense that if you don't give chunk size, the chunk size is proportional to the number of unassigned iterations divided by the number of threads, so typically can decrease, okay, as soon as the counter of iterations goes on. And then you have runtime or default. Default is equal to says nothing, as I did before in the example. Runtime means that you can set the policy at runtime either via this environmental variable you define in the shell, export OMP schedule equal whatever, or you can set by an OpenMP call OMP set the schedule just before the parallel region and whatever you want. So you can have different type of scheduling in different for cycles. It is possible to modify the behavior of the parallel region. For instance, you can have pragma and p parallel if whatever. So that means that you create a parallel region only if this condition is met. For instance, not to have that much behavior. Let's say in this case, it's really worth to have all the overhead of creating the threads and then rejoin the threads if n is 100? No, absolutely not. So I could have put here for blah, 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 if n larger than 1 billion. Otherwise, it's meaningless. No? It is, the overhead is more than what you gain from parallelism. No? That is the rationale about this. Or, in any case, any valid C expression, whatever it is. Okay? For instance, if some I don't know, device is busy or not, I don't know. So whatever is valid and valid expression in C can be put there and has this effect. You can change the number of threads directly here in the pragma, and or you can set the number of threads just before. This is a function, a call function. This is equivalent to this. Okay.
Sorry, how should I fix the number of threads?
How?
No, the number, how do I decide?
Okay, the rational. But well, normally it is the number of cores. So the golden rule is not to put more than one thread on a core. Or, unless some, I don't know what kind of condition, yeah. But in any case, it's up to you. You can, let's say that you want to balance the overhead of thread creation and, I don't know, synchronization, depending on the size of the problem, for instance, no? So you know your problem, say, okay, you calculate n as a function of the problem, for instance. The point is that now I'm showing you really basic OpenMP and really an introduction, just to, because I mean it's more important that you understand the running model and the memory model of OpenMP, the philosophy, and then you just go for, I mean, just deeper in details by yourself. Okay, but I mean, the advanced OpenMP have, for instance, you can define different parallel regions that correspond to different tasks. And so you may want to assign a different number of threads. So you have a given number of cores. So that's the maximum number of threads that you have at hands, no?
Different area would be...
Exactly. So, and that depends on what you're doing and so on. Okay. So it depends, right? Okay. In this way you can control. Okay. Well, these are other clauses. So schedule, you already know. Ordered means that everything is guaranteed to be in order of the thread ID. Then private, first private, last private. Shared, you already know. And then reduction, collapse, and away. These one are the new one that we'll talk about. So private, actually you know even this. So the variable that are listed here will be private to each thread. That means that they are not the same variable that are outside of the thread, but they are a copy of, I mean, a different variable, but with the same name, okay? And they will not exist outside the memory region. First private means the same thing, but they are initialized with the value that the variable with that name has outside the parallel region at the moment of the creation of the parallel region. So here, if I have an I without this int here, okay, if I have an I equal 10, okay, and I say here first private I, then here, if I do not initialize I, then I is supposed to be 10 if I put first private, okay? If I put private I have to initialize it here, otherwise it could be just crap, okay? And last private means the same, so you create a private variable that has the names that are listed here, but that variables that exist outside, otherwise, I mean, this is an error. The variable that is outside the parallel region will have, at the end of the parallel region, the same value that has the last thread that was active in the parallel region. For instance, again, the I that in the loop before, if I tell him it's last private I, well, at the end of the loop, it will have the, what happens? So you have that thread 0 goes from 0 to 24, no? Thread 1 from 25 to 49, and so on, okay? So let's say that 1 is the last one. So the I will have the value of 49, okay? Because it's not, I mean, it's not guaranteed who will be the last one. So, and for some reason you may want to, for instance, let's say that the threads are reading some kind of device or input, whatever, and I don't know, you want to just that that variable keeps absolutely the very last value. I don't know, so it depends. So you have this possibility. Reduction, now we come to this. Collapse. So that's important. If you have a nested loop like this, okay, you can put a pragma here. This is in Fortran. Okay, you can put a directive here or a directive here. Okay, what you choose. So if you put a directive here in the inner loop, actually what you have, that you have all the overhead of creating the parallel region and joining all the threads for n times. Okay, for at every iteration of the outer loop, you have to create a parallel region and then to destroy the parallel region, which can be a huge overhead. Okay, so normally what you do is to parallelize only the outer loop. It means that you have to keep this in mind and to design your loops accordingly. Okay, so that is the most effective way to do. However, with this collapse, you instruct the compiler to restructure the loops so that also this one is parallelized. Because what happens here without the collapse, okay, is that what you are dispatching to the different threads is an entire loop. Okay, because you are parallelizing the outer loop. So let's say that you has a schedule static with chunk size 1. Okay, so you have that the loop 0 will do that. Okay, and then the loop 1 will do that again. So then it depends on, I mean, whether or not they do the same thing depends on this. I don't know, whatever it is, but to be clear, let's say that you have 4 on the I from, I don't know, from 0 up to 10, whatever it is. And then here you have 4j from 10 to the I up to 10 to the I plus 10. I don't know, okay? So if you parallelize this, it happens that task 0 will go from 10 to 0 to 10. So from 1 to 10. Task 1 will go from 10 to 20, to 19, okay. And task 3 will go from 1,000 up to 1,010, and so on, okay? But the entire loop, okay, because you are dispatching, I mean, these are objects, okay? You are dispatching the objects for each iterations. If you put the collapse there, you are instructing the compiler to consider that even these are iterations. So you have 10 iterations here, 10 iterations here. So you have actually 100 iterations, and it is 100 iterations that must be dispatched. So shared among the threads, not 10. Is that clear, the concept? Okay, if you have 3 nested loops, you can put here collapse 3, of course. And so the compiler will count for you, okay, how to dispatch all the actual iterations, and not to consider whatever is inside this iteration as a whole object that must be dispatched to a thread. No way means that you want the threads to ignore the implicit barriers that are at the end of the parallel region of the work sharing. So when a parallel region ends, there is an implicit barrier. It means that a thread that reaches that point, just wait for all the other threads to reach the point. You may incur in some kind of overhead for this. No? For instance, after that parallel region, there might be some kind of operations and then another parallel region. Or you can have nested parallel region, okay? You can have something like a parallel region, okay? And you can have a 4 here, then something to do, and another 4 here, okay? So actually, this is a parallel construct with an implicit barrier at the end. But it may be, depends on what the code is doing, actually, that is much more efficient, that a thread doesn't wait for all the threads here, but just continue, because you are inside the parallel region, so he's continuing to, performing some job, and then enters again in a 4, and so on, okay? You can achieve this with a no wait. Otherwise, all the threads will wait here, and all the threads will wait here, and so on. And then, of course, at the end of this parallel region. So you can put a no wait, and even here a no wait, okay? But here is actually meaningless, because at this point, of course, it has to wait, because it must be destroyed with all these brothers, okay? So reduction, now we'll see an example, actually. Yeah, this is something that I've already said. So this parallel constructor, so the 4, mainly the 4 you've seen, amounts to create basically what is called SPMD. So single program, because the code is the same, and multiple data instance. So the code here is the same, but you have multiple instances, so the multiple threads that execute that program on multiple data, okay? And actually, there are other work sharing constructs, that is sections and tasks, that in which you are not sharing possibly the same code. As I said before, no, it may be that you want to you conceive your problem as task, no? Separate task, and you can dispatch these tasks to different threads, so that the threads will actually execute different codes, okay? So this is a different concept, right? This is procedural, okay? You have the same procedure, just you subdivide the data in chunks, and these are different procedures, okay? And this is quite advanced. We will not cover this, because it takes several days of example, exercise, and understanding. This is quite complicated. But it is very, very effective, because it is strictly related to the directed acyclic graph representation of work, which is not linked to procedure, so operation that you have to perform, but to problems that you want to solve. No? You may think in this way. So this is a task, okay, which is this is another task, task 1, task 0. You have task 2. So task 1 and task 2 depends on task 0, but they are independent on each other, okay? So you have a code related to this problem, to this task, and different codes for this. No? And each one with acts on some data set or the same data set. That depends. I don't know. So you may want to say that, okay, a thread is executing this, and then 2 other threads are executing, waiting for this one to finish, no? Are executing these ones. This is quite a simple case. You may have a lot of, this is task 3, and then you have other tasks, and so on. No? And then you have your graph, must be acyclic, so cannot be something like this, okay? And you can think in these terms and write a code that acts in these terms, and OpenMP allows you actually to orchestrating this workflow, okay? So there are two different concepts. Okay, so data race. This instruction, okay, here. Now we want to sum up all the elements in an array. So if I do something like this, pragma and parallel for implicit known and shared, everything, because I want A to be shared, because it's the array that I want to access. N must be shared, of course, and sum must be shared, because at the end I want to know the sum, okay? If I do something like this, this is a data race. Because I'm, of course, I'm dispatching chunk of works to the different threads, and then each thread is trying to read the sum, because there is a reading here, because I have to read the value of a sum. I read the value of AI, and then I want to write back on the sum. Of course, this is a data race. Okay. So how can you solve this problem. So let's try. What we can do is exactly the same, but now I'm adding this inside the 4. This declare a critical region, and you can put a name of a critical region in. So critical means that just, you remember, just one thread can execute this instruction at a time. It's called a lock. Okay. If you program using directly the pthread libraries, OpenMP uses the pthread libraries actually. You have to do that by hands. Okay. OpenMP just hides the details for you, and this is what OpenMP critical is about. So this works. Okay. In this case, just one line, you could have used atomic. Critical means a region, so you can put a brace with a lot of instruction, blah, 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 and the whole region is critical. If it's just one line, it's better to use OMP atomic, actually, okay? It's a matter, but well, okay. And actually, does this scale? A nice exercise that we do not have time, but we can try, or you can try yourself, is to go to a node of your cluster and to run this code, which is O2A, now I'll show you, and run this code for the same problem size, 1 billion, whatever it is, no? And with 2 threads, 4 threads, 8 threads, 10 threads, and then calculate the overhead as I shown you before, no? And to see what happens. You should find that that number, no, that serial fraction increases with the number of processes. Why is this? Because at every iteration, all the processes have to orchestrate, because just one of them can enter and execute that instruction, and all the others have to wait. Wait how many? Absolutely. How many? You have to wait p minus 1 if p is the number of threads. Okay. So just to perform one of my operations, I have to wait p minus 1 times the delay that it takes, which is, say that it's fixed. Okay. So proportional to, so you have, when you increase p, it increases the times that I have to wait to perform one of my operations. So this is an awful scaling, of course, right? It works, it's correct, but it is an awful scaling. And the related code is Y02A, okay. Sum of an array, no scaling, okay? Well, of course, this is not the correct answer. Why? Okay, why is this what I've just said? And there is this is a so normal problem, so common problem, that OpenMP has a solution built in, which is called the close, the reduction clause. Okay, so yeah, now the shared clause is not even here because the implicit assumptions are good enough for us. So the reduction means that you declare that inside this parallel region there will be an operation, that is this one, okay, on a shared variable. So what actually happens underneath is that OpenMP creates some private mechanism, okay, so you are actually not accessing the shared variable all the time, but just a private variable, and automatically at the end of the parallel region everything is synchronized and summed up, okay? That's what happens actually, not quite understand. So the reduction operation, the possible reductions operations are this one, plus multiply, minus, max, min, and these logical or bitwise operations, okay? Actually, what is interesting is that the initial values of ours is taken into account at the end of the parallel for. So in this case, for instance, if you have the reduction plus, the summation could have had some initial value, okay? It is added at the end, not at the beginning. And so is for the minimum and maximum and so on, just a detail. So here, okay. So here we have solved the problem, and you have in this respect exercise 2.
Can I ask you
Yeah.
just, here the summation is split in different components, then it is summed up at the end
Yeah.
automatically.
Yes.
I may do the same manually, let's say.
In fact, that's what I'm showing you in the next examples.
Okay.
Yeah.
No, I was wondering what is better.
Yeah, exactly. That's a good question. So now let's just go to O2, sum of an array. Okay. This one, because I just also want to show you something about how to measure time, to perform the timing of these programs. Okay, this quite simple task. So if check whether or not you're giving an argument, fine. It allocates the memory, check that the memory exists, and then just gives you some information about whether you see this is the usage of an OpenMP or not. So if you're not compiling with OpenMP, this doesn't exist. So the code that will warn you, pay attention, this is serial summation, okay, because you didn't compile with OpenMP. Instead, if it exists, then you open a parallel region, and the master just find out how many threads that will be used, and just gives you the information. You see that this is an entire region that is executed just by the master, not only an instruction. So then you initialize the array with random numbers, and then you calculate. How you calculate? If you are not compiling with OpenMP activated, is this. Okay, very stupid implementation, not particularly performant. And instead, if you are compiling with OpenMP activated, you do that, okay? Exactly what is shown you on the slide. You perform also a timing here, okay? How is it made? By usage of this, here. This is just a macro. I'm using clock get time. This type of timer gives you the CPU time used by the process. This is not the wall clock time, okay? Because during the wall clock time, your machine, above all if it's your laptop that is doing a lot of stuff, you know, while you are executing the code, a lot of kernel space, whatever, blah, blah, blah. But even in the HPC facilities, okay, the kernel is doing something while you operate. So you are just counting for the CPU time used by the process, not by kernel, okay, which is different. So it is, of course, an monotonically increasing counter. So you take the time, the value of that counter at the start, at the end, and then you print the difference, and the difference gives you in second. Okay, actually it is in. Pay attention that this is. It has two fields. These are two long integer fields, one for seconds and one for nanoseconds. Okay. So you have just to take in account of this, and that's it. Okay. So now let's go.